Welcome back. Today we will review an essential topic that we need to understand projectile motion, vectors. We will begin by recalling what they are and see how we split them into what we call vector components. Let me show you quickly how important they are in this lesson. Look at this diagram. You will have plenty of this. And at the end of this lesson, you should be able to understand what each arrow there represents. And then make your own illustration like that when given a worded problem. Let's begin with that. An example problem. How far is the ball in the horizontal a second after it is given an initial velocity of 15 meters per second at 30 degrees with the horizontal? 15 meters per second at 30 degrees is a vector. Vectors are these quantities, those that are more accurate only if they are described with a direction. The symbol is telling you that it is a vector if the quantity has that arrow above its symbol or it is written in bold. Another way to write vectors is by illustrating them as arrows. A displacement, for example, of 5 meters east will look like that, while 10 meters north is like this one. See that the length of one is twice the other? Right, the length represents the magnitude. And the arrow points to the direction, that indicate what quantity it is with the proper symbol for displacement. Most of the time, you will use the arrows because that is the only way to analyze them. Another thing we need to review before we continue is, how do we determine the direction? Look at this scenario. Let us say we are observing a rock falling off a cliff. To begin describing its position, you need a reference point. You may describe its position from the edge of the cliff or from the ground. After you set the reference point, the next step is find a way to make sense of the space, like turn that into a map that we can understand. What better method than a Cartesian plane? This is one of the many reasons why the Cartesian plane is an amazing invention in mathematics. Your x-axis for left and right movement and the y-axis for up and down. To do that, to determine the direction, place the origin at your reference point. Based on that, any quantity of the object that is directed to the left is negative, while anything toward the right is positive. In the same way, any vector of the object that is downward from your reference point is negative, while upward is positive. Let's try that in describing that rock. Let's begin with this first case. Based on this reference point, the edge of the cliff, that is negative 5 meters, y-axis. Look at how it is written. Just based on that mathematical statement, it is telling us already that it is a vector. It is also a displacement. From there, you can also see that it is in the vertical. It is in the negative of the reference point. Down because it says y-axis. How far down? 5 meters. If the reference point is here in this case too, based on the ground, that point is positive 10 meters, y-axis. And capture all those descriptions in a symbol like that. That negative and positive directions you have indicated do not really matter out there. It is the same observation. Let me show you. Let's say after a second, this rock is already there. Measuring it from the cliff, you say the change is negative 1 meter. See, from negative 5 to negative 6? That's a change of negative 1. Measuring it from the ground, you say the change is negative 1 meter as well. Because see, from 10 meters to 9 meters. It is the same because no matter how you describe it as positive or negative for you or the other, in reality, it is just this going down for both. Now that we know the symbol of how to write the values with the direction indicated, using positive and negative, there is one last thing we need to know, vector components. Let me illustrate it through vector addition. Let us say we will combine two vectors using this question. What single displacement is equal to a movement of 5 meters east and 10 meters north? If we use arrows, it will look like this. Here is the starting point, then you go 5 meters east, then continue 10 meters north. In the end point is here. That single displacement is this vector from starting point to the end point. If we look closely, what we have here is a right triangle. You can use the then Pythagorean theorem to find that displacement here and your trigonometry to find this angle. So instead of walking 5 meters east then 10 meters north, just go 11.18 meters at 63.43 degrees north of east. You will end up in the same place. What this illustrates is that you can combine vectors. If we can combine vectors to 1, can we split 1 to 2? Yes, we can do that, and we call them vector components. Sometimes, the vector that is given to you is neither in the x-axis nor in the y-axis, like the preceding examples we solved. Sometimes it looks like this. Let's label it as another kind of vector. Let's have velocity this time. When is this possible? A cannonball is launched with a velocity of 12 meters per second at some angle. Yeah, that kind of situation. Just why we need to break this velocity vector into two? Doesn't it complicate it? Well, for projectile motion, we need to separate how it is moving in the x from how it is moving in the y. Because it is simpler that way when they are separate. How are we going to do that? Okay, it is somehow the reverse of what we did a while back in vector addition. Find the two vectors that when combined will result to that velocity vector. Looking at the figure in the left, those vectors are these. Okay, we call this one as the vector component in the x, while this one is the vector component in the y. These two pairs are the easiest because they are parallel to the axis. What I mean is, you can come up with other pairs of vectors that will result to this one, but the easiest pair are those that are located in the axis. The hypotenuse v is the same as these two components when combined, this x and y components. This is only one way of showing it. Let me show you another one. This way. Sometimes it is also presented this way. Notice that here, the components are placed at the same point with a given vector. It is easier to analyze this way. Okay, I think that's it. I think we are ready. Let's put the diagram back. One good measure, if your knowledge of vector is enough to begin studying projectile, is by trying to make sense of the following. See the orange arrows and the way they are labeled? Okay, try to compare that with the rest of the orange arrows. Now, take a look at these blue arrows, the way they are labeled, compare that with other blue arrows, and also with the orange arrows. How about these green arrows? Compare that with the green arrows, with the blue ones, and the orange ones. Can you make sense of all this information? If you can make sense of these figures, I hope you realize that indeed mathematics, its numbers, symbols, and diagrams is a language, that by just looking at this picture, you get a lot of information already. You need that skill because projectile motion demands a good analysis of two kinds of motion that are happening at the same time. These are uniform velocity in the horizontal and uniform rate of change of velocity in the vertical. Let's go back now to the problem that was given from the beginning of this lesson and see if you are ready to use this language to elaborate on what the problem is trying to say. How far is the ball in the horizontal a second after it is given an initial velocity of 15 meters per second at 30 degrees with the horizontal? What do you think? Show your answer and be awesome by showing as well the diagrams of the vectors involved.